Good afternoon. We're going to go ahead and get started. My name is Maya Cooper. I'm a senior research scientist at Johnson Space Center in the Food Lab. I am not Dr. Grace Douglas, but I will moderate this session for you today. I'd like to welcome you to the food and nutrition session. We have 4 exciting talks for you today. Our first talk will be from Tim Boulette of University of Massachusetts Amherst on degradation of vitamins in food.
Thank you all for coming to arguably the best session of the whole conference. You really got to save it to the end, save the best for last. So, this actually marks my 3rd, and it will be my final year presenting our my work together with UMass Amherst and together with NASA on using predictive models to understand the degradation kinetics of vitamins that they're interested in the foods that they're interested in during thermal process and during storage. Now, what I normally would do in the past 2 years, what I've done is I really go into depth in doing a step-by-step on how to take a data set and determine the kinetic parameters from that data set. And when we understand those degradation parameters, we can fully understand how the degradation of vitamins relates to temperature and time. But I think that's been pretty well established. So what I'm going to do instead is I'm going to discuss representative data sets for when the model is working very well, our endpoints method model. And that's typically when we're talking about our vitamin B1 food products. I'm also going to talk about a data set in which we see that our endpoints method model is not working quite as well, and that's generally with our high acid foods and vitamin C. And then what I'm also going to do is I'm going to talk about another version of the endpoints method model that we have dealing with non-isothermal data. So that typically has to deal with thermal processing and when storage temperature isn't so easily controllable. If you are still interested in understanding kind of the background mathematics, the justification for our approach and things like that, feel free to visit demonstrations.wolfram, and you can search Miha Peleg or Mark Norman, and that will populate a bunch of their programs, some of which we worked on. And within each of those programs, it really defines the underlying mathematics, the assumptions that we make, and some of the chemistry that go into the construction of each program. So what we actually did is we created a program with a predictive model built into it. It's more of an app more than anything. And what the intention is to give this to NASA at the Advanced Food Technology program and allow them to quickly, cheaply, and easily discern the degradation of those vitamins that they're interested in and the foods that they're interested in. So yeah, we want to really give that to them and give them the tools that they need to understand the degradation. When we first made the program, we confirmed it against published data sets. And those data sets that really exist out there have to do with model systems and simple food systems like juice. But what we needed to do is try to make sure that our model is robust enough to handle complex food matrices. And of course, that's what NASA wants to do. So what we had to do is utilize our program to track and then make predictions on what degradation we expect to see during thermal process and during storage. So like I said, I'm not going to really go into the background mathematics, the justification or anything, but what I want to do is highlight that what we're really looking for is we want to understand what the degradation rate constant K is at a reference temperature. And we want to understand how that reference or how that degradation rate constant changes with changes in temperature. And that's described by our temperature sensitivity term C. When we understand those parameters, we're able to create optimum thermal processes and storage strategies, talking mainly about refrigeration and things like that, based on those unique kinetics. Some of you may be asking yourself, well, why vitamin C and B1? Of course, those are really important vitamins to get in one's diet. They're not necessarily hard to get in one's diet if you're eating fresh food, but in stored food, these food vitamins can be really susceptible to degradation, particularly at high pHs. And when I say high pH, I'm talking in the 4s and above. 4.5 and above is typically critical instability for a lot of these vitamins, especially vitamin C. And they're also heat labile, so temperature will degrade them pretty rapidly. So for our particular experiment, we were provided with 3 NASA recipes that are representative for each vitamin. So for thiamine or vitamin B1, we have brown rice, split pea soup, barbecue beef brisket. For ascorbic acid or vitamin C, we have strawberries, rhubarb applesauce with a pH variation plus or minus 0.5. So that's 3 versions of that rhubarb applesauce. And we have sugar snap peas. For all of these foods, we would either differentially retort them, or freeze dry them, or pre-process and freeze dry them, and then enter them into storage at 4 degrees, 20 degrees, 37 degrees for 2 years, periodically measure the vitamin content, and create predictive models with that data. So the two versions, as I mentioned at the very beginning, we have isothermal version, which is more appropriate for long-term storage, understanding the degradation you have with static temperature. And then we have a non-isothermal version, which is more applicable for thermal processing or when your storage is not easily controlled in terms of temperature. So as I said, I'm going to go now into an example of a data set where we have really good model fitting. So for brown rice, looking at vitamin B1, what we are getting is about 78 micrograms of thymine retention in our thermal process versions at the initial time point. And of course, what you observe is at a higher temperature storage, you get a more rapid degradation. That just makes sense thermodynamically. Looking at the freeze-dried versions, what we see is a better retention of those vitamins right off on the onset. So we're looking at like 110, 115 micrograms of thymine to start. And then once again, you see an increased degradation as you increase the temperature. The reason why we don't have data here for the 24 months, it's not because it just dropped off to zero, it's just we're still processing that data now. In terms of constructing the model, I wanted to demonstrate that these models are constructed using data from only 9 and 12 months of storage at our temperatures. So using data only accrued from 9 to 12 months, we're able to produce a less than 5% difference at 24 months for our thermal process product, and less than 5% difference at 21 months for our freeze-dried product. Now looking at our vitamin C data, what we're getting for vitamin C in our rhubarb applesauce pH 4 after thermal processing is we get a retention of a little over 4 milligrams per 100 gram, that's the serving. And then once again, as you increase the temperature, we get a significant drop off. But it's important to note that the difference between the 4 and 20 degrees is not significant, seemingly not significant, but once you reach a critical temperature, it seemingly drops off. And this is again, thermal processed rhubarb applesauce. So moving on over to freeze-dried versions, what we see is about 10 times the increased retention in that vitamin C. So definitely a good process for the preservation of vitamin C. Once again though, we still have susceptibility to temperature and we see a drop off at 37, pretty rapid. Now before I get into the actual modeling of the vitamin C, I want to mention that we're considering a modification to that original model for cases where there are multiple fixed first order kinetic events. And what I mean by that is, in the case of vitamin C analysis, or I should say vitamin C just degradation in general, you have ascorbic acid, which degrades aerobically into dihydroascorbic acid. That degradation is rapid, and it's very temperature susceptible, and so ascorbic acid is very labile to degradation. However, dihydroascorbic acid is not as sensitive, and its degradation is anaerobic and is much slower, and it adopts a somewhat higher non-zero asymptotic behavior when you measure it. So what we did was we implemented an asymptotic consideration in the modeling for vitamin C, and in our thermal processed foods, we see a significant improvement in the fit between the data points and actually our model compared to the original endpoints method, which doesn't factor in that second degradation product. So I want to take the opportunity to go over what those differences are between our thermal process product degradation kinetics and our freeze-dried versions. So looking at brown rice specifically now, so we're looking at vitamin B1's degradation. The degradation rate constant K at 25 degrees Celsius, it stays about the same upon freeze drying. So you're not getting a huge improvement in slowing down that degradation, but what you are getting is you're getting a lower temperature sensitivity. So what that really means is if you modify the temperature plus or minus a degree, how much is your intrinsic degradation rate going to change? So what this shows is upon freeze drying that brown rice, you're going to get the degradation you're going to get at a reference temperature of 25 C, but if you refrigerate it, the benefit is not so much there for the freeze dry. Like the need to refrigerate kind of goes away. And at the same time, temperature abuse, high temperature abuse won't have as much of an effect. So in terms of storage strategies for freeze-dried brown rice, you don't really have to worry as much about investing energy into refrigeration. However, there is something interesting about the differences between the effect of freeze-drying on B1 and C. So as you can see, we're looking at rhubarb applesauce now. What happens upon freeze-drying is the intrinsic degradation rate constant nearly halves at our reference temperature. So at a little bit above room temperature, we get an intrinsic degradation that's much slower, but we get a large increase in the temperature sensitivity. So what that means is when you freeze dry the product, if that product experiences temperature fluctuation, that degradation rate is going to change rapidly. That vitamin C will degrade much more rapidly if you expose it to thermal abuse. So now what I'm going to go over is the thermal processing modeling, and that's something I really haven't discussed much in the past, but there shows some promising results here. So in order to conduct this modeling, what we need to do is produce thermal profiles that significantly differ in their exposure to temperature, the total process time, and max temperature, such that we can interpolate the relationship between those factors and the degradation in the vitamins that we observe. So in doing that, we produce 3 thermal processes, which we call high temperature short time, moderate temperature moderate time, low temperature long time. So we process the same food by these three processes, and these are the concentrations that we end up for vitamin B1 in brown rice. So what I've also shown here is the equivalent lethality, which that is talking more about the equivalent kill you're getting for pathogens and botulism, specifically botulinum. Even though that's not a direct correlation, what it does give us a sense of is the thermal penetration. So what we're seeing is the moderate time, moderate process has a significantly higher thermal penetration, essentially, compared to the other 2 profiles. And interestingly enough, even though the high temperature and the low temperature process differ significantly in their construction, the thermal penetration is nearly equal. So that gives us a sense of what we can expect to see in terms of the vitamin retention. And we do see kind of like a one-to-one here. So now as far as constructing the model goes and determining the kinetic parameters that will allow us to predict vitamin content in any process, we can just grab, I think it's frozen. Oh, I might have gotten it. Right, I got it. Thanks. So in terms of modeling and the production of those kinetic parameters that help us identify the degradation, we just need a pair of concentration retention ratios here on the right, and we need the thermal profiles. So we can import those into our program. So these have been imported through our program, and we enter in our concentration ratios here, and they'll show themselves as endpoints in the bottom module. And then what you want to do is you want to kind of play around with the K and C values, which it basically describes the entire relationship between the degradation rate and temperature. And what's going to happen is we're going to get trajectories that paint themselves out in the bottom module. And once you find a K and C pair that produces trajectories that match both cases, that's a good indication of that's the relationship, the temperature relationship. So that is with our high temperature and moderate temperature process or profile. We can switch one of those out and we can repeat the process. So in this case, we have these as endpoints and we get K and C values that more or less agree with the previous pair. So that's a good indication of, again, we're getting a good fit. And we're getting a good indication of that those are the real degradation parameters. We do it a third time. And what we can do now to make predictions on what kind of degradation we're going to observe in a given process is we can take the degradation parameters of 1, or the average, and then plug these into the equation with the new process, and it will tell us basically what concentrations we're expecting. If we do this with using the pairs we have here to predict C, and then here to predict B, and here to predict A, we get an experimental versus predicted that's essentially within measurement variation. So that's a very good sign. And going down to looking at vitamin C, what we see is more of the same. So we're able to make predictions using 2 profiles. We can make predictions about the third that's within the measurement variation. So very promising. And what that also means is if you want to test a new process, a new profile, and you know what the temperature exposure is going to be, you can put that in the program and predict without having to do it what kind of vitamin loss you're going to obtain. And I also wanted to mention an interesting thing here. You'll notice that compared to the brown rice vitamin B1 degradation that we see with our low temperature long time process, you get more degradation in the rhubarb applesauce of vitamin C when you do the low temperature long time process. And that indicates to us that the temperature sensitivity in process for vitamin C is not as strong as it is in vitamin B1. It's more just exposure time in general. So exposure to heat in general degrades vitamin C, which of course makes a lot of sense for the suggestion of pasteurization techniques. Also suggesting that high temperature short time is probably ideal. So in summary, each of our models, the isothermal and non-isothermal models, are able to generate predictions using only 2 time temperature profiles and 2 concentration ratios. The original isothermal version fit very well with vitamin B1 loss. If we can consider asymptotic behavior for vitamin C loss, again, taking into consideration that dihydroascorbic acid resilience, it improves the fit dramatically for vitamin C. I think very importantly, freeze drying was a very effective tool for the protection of the vitamin loss during preservation. So we get about 33% increase in B1, 900% increase in C, so very valuable for C compared to the retort thermal processing. But again, degradation kinetics and the way that they change and the temperature sensitivity don't necessarily reflect what you'd expect. So it's important to understand that relationship. And so also the non-isothermal version using non-isothermal data was very effective in predicting vitamin loss during retorting. So moving forward, I think what needs to happen generally is that we need to be able to account better for those multiple fixed first order kinetic events. So ascorbic acid into dihydroascorbic acid and so on. Because the limitation there is mainly in the measurement. Creating a reducing environment so that you don't lose ascorbic acid actually reduces that dihydroascorbic acid back into ascorbic acid. So there's a limitation there that needs to be factored in. Also, we observed between foods, like I mentioned, split pea soup, beef brisket, there are food matrix variations between those that contribute significantly to the degradation kinetics. And in freeze drying, it alters the degradation kinetics in ways that are hard to anticipate, but it's also dependent on the nutrient chemistry, the compounds chemistry. And it's worth mentioning that freeze drying is essentially changing one of the food matrix properties and lowering the moisture content. It also concentrates salts, it concentrates other things. So what I think ultimately we need to do is discern the most significant physical chemical properties of the food that are factoring into these chemical shifts, these degradation changes, and why one becomes more temperature sensitive than the other. And if we can do that, we can better predict the degradation kinetics for any food. Thank you.
If there are any questions, please go to the mic at this discussion. No question? Okay, thanks.
Thanks, Mike.
Our next talk will be brought by Dr. Sarah Swartz.
I'm going to share it with the screen.
All right, thank you. It's a pleasure to be here today, presenting on behalf of Dr. Smith. I'm going to be presenting results today from our biochem profile study, and particularly focus on vitamins. So when you think about nutrition, it's important to step back and remember what we've learned from history. During the age of sail, which spans from the time of Columbus's voyage to the invention of the steam engine, over 2 million sailors lost their lives from a single nutrient deficiency, which was vitamin C. They died of scurvy. There are numerous other examples of toxicities, vitamin A toxicity during the exploration era, or lead poisoning from the tin cans that were prepared. So we obviously don't want to repeat history, and we know what nutrients we're going to need. We want to make darn sure that we provide those nutrients and assure that they're stable in the food system as well for very long missions. And the food lab at NASA is working very hard on that. So the data today I'm going to present really comes from 3 different data sources. One is our operational data, the clinical nutritional assessment, where we collect from all crew members from Expedition 1 up until present. And it involves collection of urine and blood markers before and after spaceflight. There's no data collection in flight for samples, so we do collect food intake. We now collect food intake from a food intake tracker app, an iPad app that was launched a couple years ago. So we are getting where the crew members record all food intake for their entire mission. Before that, it was a food frequency questionnaire completed once a week. In 2006, we had a nutrition SMO experiment. NASA used for experiments and for a supplemental medical objective. And at that point, they launched a centrifuge and -80 freezer on board ISS, which allowed us to collect blood and urine samples. And that study morphed into what we call today biochemical profile. So some of those tests were cut out. Vitamins is one that has remained. So we collect that operationally, and then we started in 2006. Most crew members from then to today. And our last crew member from biochemical profile landed in the past month. Here's some photos of our crew members taking samples, blood samples. Here's a single mode urine, putting the samples in the centrifuge and then in the -80 freezer. So as I mentioned today, I'm going to focus on the vitamin results from these studies and just kind of walk you through a few examples. So first off, vitamin D. Vitamin D is we've long been concerned about just because we know that there's not enough in the food system. We can't synthesize vitamin D because there's no ultraviolet light exposure shielded by the spaceship craft. So vitamin D from Expedition 1 up until 2006, all crew members had access to a supplement containing 400 IUs of vitamin D per day. They say they had access, not all took the vitamin D, but they did have access. And we found with most of those crew members, their status decreased after flight. Some of them decreased below the point of what we call deficiency, which concerned us. At that point, you could start seeing clinical symptoms, osteomalacia in adults or even rickets in kids. We definitely didn't want to get that low. So in 2006, which is also when our nutrition SMO experiment started, we recommended just taking 2 of those supplements. So they were taking 800 IUs of vitamin D per day. And so this purple line here shows those data where you see pre-flight, their status is good. And if they're taking 800 IUs per day during their 4 to 6 month mission, they were able to maintain status at about 80 nanomoles per liter, which is what we were aiming for. Looking at vitamin B12, so we have methylmalonic acid on the left here, vitamin B12 intake on the right. Methylmalonic acid is a gold standard functional indicator of vitamin B12 status. We do also measure serum B12, I'm going to show you the MMA here today from 55 crew members. So if you look at MMA, the higher the number, the more deficient with vitamin D. So you don't want to have values outside this high end. And so we have seen a handful of subjects, crew members with a vitamin B12 deficiency before and during flight. If you look at the dietary intake, you can see here that the dietary requirement has been met on 89% of flight days, which is excellent, I'd say. There are a handful of crew members you can see that definitely supplement, and this is up their own choice with consultation with their flight doc. And we've got some that are 40,000% of their recommended intake. Switching over to folate. Red blood cell folate is a long-term indicator of folate status. We've got raw data on the left and percent change on the right. And if you look at the percent change comparing pre-flight to landing day, 70% of the crew members decrease status after flight. And most of them do stay within the normal range. Some do scrape the bottom and are at the very end of the normal range. So looking at folate, serum folate, again, raw data on the left, percent change on the right. Serum folate's a more transient indicator, short-term folate status. But again, if you look at serum folate during flight, pretty much all crew members, their status decreases during flight, and some are scraping the bottom of the normal range. And once you get below that, you're looking at clinical deficiency symptoms. And then if we look at folate intake, dietary requirement was met on 64% of flight days. So this could contribute to the decrease in status during flight. We'll have to look at that more carefully. So we don't have the high fidelity dietary intake data on all of the crew members I showed you in the last slide, but we're going to be teasing that piece apart to see if we can see the relationship with intake and status. So folate's involved in a number of different processes, 1-carbon metabolism, in particular where it's responsible for moving one carbon units from one molecule to another. It's involved in DNA repair and synthesis. It's involved in maintaining endothelial function, nitric oxide production. So really, we need to be looking at these vitamins in relation to clinical endpoints. One of the endpoints we looked at, teaming up with Dr. Bailey in the twin study, we looked at telomere data because of the role of folate in DNA repair and synthesis. So we looked at her data in the flight twin during flight, the telomere data in her dashed line. And if we plot that against our serum folate data, it matched it very well. I mean, just as one subject, but we're hoping to get more data with more of her telomere subjects to see how folate lines up with the changes she's seeing during flight. The last one I wanted to show you is choline. It's a B vitamin-like compound. It's required for membrane function and structure, acetylcholine production, methylation. So when you have a low choline status, it can lead to an increase in free radical release due to leaky mitochondrial membranes with increased evidence of oxidative damage or stress. And so the unique thing about your choline is that your genetics drive your requirement. So the percentage of population that need to eat choline on a regular basis, only 77% of men require choline in the diet. Otherwise, their bodies can actually make some choline. 44% of premenopausal women and 80% of postmenopausal women. The reason for that difference is that estrogen affects choline synthesis. So we look at choline intake. By the way, when the requirements for ISS were developed, choline did not have a requirement, did not have a GRI. So there was no requirement for choline. Since then, there has been. And since our dietary food intake tracker app has been launched, we are able to look at choline intake. And surprisingly, the dietary requirement is not met on most days during flight. And this obviously doesn't take into account genetics at all, so we're not genotyping everybody, but it is something we're going to keep an eye on. And as I mentioned, if you look in the literature, a low choline status is related to increased oxidative damage. So what we did with some of our data, we looked at choline intake, 4-day averages of choline intake, and plotted that against some of the urinary markers of oxidative stress that we had at the same time of the collection of these intakes. So we looked at choline intake, we looked at a urinary marker of DNA damage, 8-hydroxy-2-deoxyguanosine, and urinary prostaglandin F2 alpha, and found some relationships with a higher choline intake was associated with a lower level of oxidative stress. So in summary, nutrition is a key factor for true health and performance. Vitamins remain a concern on exploration class missions. For health and performance, we need to look at these data in light of other physiological endpoints. Especially for exploration missions, we're really concerned about that we're going to get a prolonged radiation exposure, higher ionizing radiation that we've seen before. How is that going to affect blood-brain barrier function and vitamins that are concentrated in the brain? If you have compromised blood-brain barrier function, vitamins like folate, you could potentially have a cerebral folate deficiency. And then you can go down the line and you have increased risk of depression, things like that. So we definitely need to look more at this, especially with radiation exposure, I think in environmental insults. I think that's, yeah. If anybody has any questions.
Super interesting. I was wondering, you mentioned genetics. What about the NTHFR mutation? Really big part of population.
Right. So yeah, that some people have shown that if you have the recessive genotype for FTHFR, your folate status, you require more folate. So that's another example. I think personalized nutrition, we'll get there someday, where we're going to genotype members, but I think we're pretty far off from that. So we just need to cover everybody at this point, make sure everybody's getting enough. But we don't know the genetics.
So yes, we know the people that were maybe slightly below, that whether or not that.
Correct, that's correct. Yeah.
I have a question that you said that some astronauts opted to take their different forms of nutritional supplements and previously required that other people or other astronauts maybe haven't available which was in that sense going forward and providing different types of finance and stuff. What do you think of these hurdles?
I think just education, after we show them data that their vitamin D status is going down, most are pretty open to that, and they'll take it. If you just educate what's happening, why we need to do it, I think most are pretty open to doing that.
Are there any other questions? Okay, well, let's thank Dr. Swan. So our next talk will be by Dr. Anne-Sophie Schwer, and she's going to talk to us about potential countermeasures against the effects of simulated spaceflight on multiple tissues.
Beginning.
Thank you everyone for being here, and thank you for the organizers for the opportunity to speak here today. So today I'll be talking about the potential countermeasure to prevent the damage induced by space flight. So, we all know, I don't need to tell this audience that some of the issues with spaceflight is the damage that can happen to multiple tissues, including cardiovascular, the central nervous system, eyes, and skeletal tissues. And space is really a combination of both microgravity and radiation, amongst other factors, which affect the human body. A little bit about space radiation. So the space radiation sources are galactic cosmic rays, solar particle events, and protons and electrons trapped in the Earth magnetic field. And space radiation is composed of a range of ions from low linear energy transfer, or LET, ions such as proton, and from high Z or high LET ions such as iron. Our lab and other labs have shown that radiation induces bone loss, cancellous bone loss in rodents. The cancellous bone is the spongy part of your bone, and both low LET such as gamma and proton, or high LET such as iron, induce bone loss. So you can see a 3D structure of the bone structure, and after radiation you can see less white and less trabeculate or thinner trabeculate. So we quantify this by bone volume over tissue volume, which is BVTV, and trabeculate number and thickness, which we measure with the micro-CT. And our main question was, is this preventable? A little bit about the mechanism of bone loss, radiation-induced bone loss in rodents. It's driven firstly by an increase in bone resorption by the osteoclast cells, a decrease in bone formation by the osteoblasts, increase in oxidative stress and damage, resulting in bone loss. The current methods on the ISS for bone loss prevention are resistive exercises such as the ARAT, which mimic mechanical loading, and bisphosphonate would prevent the BMD, the mineral density, but has adverse effects. And it also only acts on the bone resorbing osteoclasts. So we decided to try multiple countermeasures to prevent the bone loss. In terms of diet, so we have the control diets, CD. We tried an antioxidant cocktail diet based on Kennedy et al. We tried dry plant diet based on Halloran et al. And we measured the total antioxidant capacity of the diets. And as you can see, the antioxidant diet has increased total antioxidant capacity, as did the dry plant diet compared to their respective controls. In terms of drugs, we tried alpha-lipoic acid, an antioxidant, and ibuprofen, an anti-inflammatory. We had different schemes of radiation: 2 gray gamma, 1 gray of dual ion, half proton and half iron to stimulate space radiation, and 1 gray iron has a positive dose, positive control dose. So, as you can see, after radiation, mice with the control diet had bone loss, it's measured by BVTD, but mice given the ibuprofen or the DHLA did not rescue that bone loss. Mice with the antioxidant diet also did not prevent that bone loss. Whereas mice with the dry plant diet, as you can see, had a nice rescue of the BVTD. So this is important just to notice that not all antioxidants are equal or effective. In terms of the mechanism, the dry plant diet prevents the early increase in gene expression related to osteoclasts. As you can see here, rank-ligan increase in mice with the control diet, but mice with the dry plant diet prevent that increase. And so rank-ligan and MCP1 are 2 markers of osteoclasts, and it also prevented TNF-alpha, inflammation, and NRF2 oxidative stress. Furthermore, when we tried with the higher dose of 1 gray iron, mice with the control diet had bone loss, mice with the dry plant diet rescued completely this, in addition to having an anabolic effect. Furthermore, one of the major issues is the deterrence to the osteoblast, the bone-forming cell. So after exposure to 1 gray iron, mice with the control diet had a decrease in the osteoblast cell growth and differentiation as measured by the osteoblast colony counts and mineralization, whereas mice with the dry plant diet prevented that decrement. So pretty promising. In addition, we measured oxidative damage as measured by MDA by doing T-bars in the serum. And as you can see, mice with the control diet after radiation have an increase in MDA levels, whereas mice with the dry plant diet don't. This points towards a potential broader radiation countermeasure for multiple tissues. So far we can say that the dry plant diet acts on the bone resorption, prevents the detriment to the bone formation, prevents oxidative stress and damage increase, therefore preventing the bone loss due to radiation. But how about stimulated microgravity and the combination of stimulated microgravity with radiation? So this is our experiment design that we did. So we started feeding the mice 14 days before the start of HU, high limb loading, as you can see the model for stimulated microgravity. On day 3, we irradiated with gamma, and on day 14, we did pure tissue collection as well as osteoblastogenesis. We either fed the mice controlled diet or dry plant diet, normally loaded them, high limb loaded them, sham irradiated them or irradiated them, resulting in 8 groups with an N of 10 per group. Here are some micro-CT images of the tibia. So you can see here on top, mice with the control diet. After radiation or HU, or the combination, you can see less trabeculae in the cancellous bone, whereas mice with the dry plant diet don't have such a detriment. The 3D rendering of the cancellous bone, you can also see that, but of course we quantified it. So this is in the tibia, the long bone. So mice with the controlled diet after radiation, or the combination of HU and radiation, have a significant decrease in BVTD, whereas mice with the dry plant diet don't sustain such a significant decrease in dry plant. In terms of trabecular thickness, so the rods, you see also a decrease after exposure to HU or HU plus IR in mice with the control diet, but not in mice fed the dry plant diet. We also looked at the femoral head and neck. Here are some representative images of the femoral head and the neck. And again, you can see mice fed the control diet have a strong decrease in bone structure, whereas mice with the dry plant, not such a decrease. We quantify this, so this is the femur head. So the BVTD is decreased with HU and HU plus IR in mice with the control diet, but does not reach significant statistics level with the dry plant diet, so prevented. And similar in the trabecular thickness. Next, we looked at the long bone, an axle bone, the vertebra. And you can see that both the BVTD, the BVTD is decreased in mice with the control diet after HU and HU. The mice with the dry plant diet don't have such a decrease, and on the contrary, there's an anabolic effect that we see again, just by feeding the dry plant diet. In terms of cortical thickness, which is important for the strength, the mechanical properties of the bone, we see a decrease with HU and HU&IR in mice with the control diet, not in the dry plant diet. We went ahead and did axial loading testing with the vertebra for maximum load and the stiffness of the bone. And mice exposed to HU and HU+IR have a strong decrease in maximum load and stiffness when fed the control diet, but fed the dry plant diet don't sustain such decrease. And here are some representative images where you can see the difference. Next, we looked at the capacity of the dry plant diet to prevent the osteoprogenitor determinants. So mice fed the control diet after exposure to HU have a decrease again in cell growth and differentiation, whereas mice with the dry plant diet prevented that decrease. So pretty promising, pretty exciting. But the third aim of the grant was actually to look at other tissues. So we took a gene expression approach, and we looked at the left ventricle from the heart, the hippocampus in the brain, the eyes, and the bone marrow cells of the animals. And we extracted RNA and did a PCR array. We did a panel of between 80 and 160 genes related to genes in aging, cardiovascular disease, neurotoxicity, and DNA damage. The wet bench is done, but the analysis is still in progress, but we have some preliminary data. So in the heart, which was the first tissue we looked at, we see the effect of the diet, but very little effect of the diet. One gene is increased and one gene is decreased due to dry plant. Loading decreases, so HU decreases 10 genes, and increases 13. Radiation increased only 3 genes and decreased 25 genes. And we have some overlaps between the diet and loading and the radiation and loading. So the analysis is still in progress, but we have some preliminary pathway analysis. So the effects of HU. Here the pathways in brown are the ones that are affected, and you can see different pathways involved. But particularly the immune system is a signal to infection as well. The effects of radiation activates DNA repair and apoptosis as expected. And the combination of both HU and IR increases the pathways in diseases, but interestingly also cancels out the effect of certain pathways seen that were activated in HU and IR alone. The combination, for example, cancels the vesicle mediated transport. The effect of diet, if you remember, there were a few genes affected, but the genes affected were metabolism and metabolism of protein. So dry plant seems like a potential space-like countermeasure. It prevents the cancer and cortical bone loss. It preserves the bone quality and strength. And it prevents the radiation-induced bone loss from both low-energy and high-energy radiation, so relevant for both spaceflight as well as radiotherapy patients. It protects the marrow-derived osteoprogenitors, which is important for mesenchymal stem cell research. And in terms of mechanism, it mitigates the early increase of post-class cytokines. It protects the bone-forming osteoblasts. It reduces oxidative stress inflammation, and is a potential multi-tissue solution. I have still a lot of tissues from this experiment, and If you're interested in any tissues, let me know. And I would like to acknowledge, of course, Ruth Globus, the best mentor you could imagine. So Cecina, we did a lot of the work, and of course, the funding. Without whom it would have been impossible. And if you have any questions.
So this is all dry plum, but is there any evidence that you know that if fresh plum is available that would have similar, I guess, results, do you think? Or do you think that there's like something about the dry being concentrated and how finding it, and also how much we have to eat them for effective?
Yes, so not with the dry plum directly, but with other fruits, there's been comparison between fresh and dried apple and mango, and it seemed that when it is dried, it's more concentrated. And we suspect it's actually something in the skin. So that might be another reason. We haven't tried it directly, but one team tried for, I think, osteoporosis-related diseases, prune juice, and it didn't work as well as dried plums as well. But yeah, we suspect it's some of the polyphenols probably in the skin.
Have there been any attempts to elucidate some sort of mechanisms how these dry plums actually preserve some of the bone acids and all these possibly by K levels and all this sort of thing?
So we show that it decreases oxidative stress and damage, which is really one of the main pathways by which the bone loss happens, we believe. But not in more details, no. A team has tried to extract the polyphenols and provide it, but it wasn't as efficient as the dry plums themselves. So it might not be as simple as just the polyphenols.
Do you say about the percentage that you're feeding them for to be effective?
Yes, so it's 25% dried plums in mice. However, in humans, there's been a couple of studies where feeding 50, 100 grams a day prevented age-related osteoporosis. And that was done, in humans, so that would equal to 5 to 10 dried plums. We have done a dosing study, and the more you lower the dose, the less effective it is. But even at 5% of dried plum, it still prevents the bone loss, but not as efficiently.
This is exciting because I grew up eating a lot of dry plums.
Yeah.
But I was wondering if Baylor has looked at developmental stage of bones in mice and cats.
Actually, I didn't get that question quite often. No, that's a good idea. We haven't thought about looking for development yet. No.
Thank you very much. Our last presentation from the day for the day will be from Mary Humrick from Kennedy Space Center, talking to us a bit about the work they've done with fresh plant produce. Also, I want to make note that our third presentation of the program will not be presented today. However, at the end of the furlough period, feel free to contact Dr. Douglas. I'm sure she'd be happy to share those results.
Thanks, everybody, for being here this afternoon. Today I'm going to talk about baseline microbial assessment of fresh produce. I come from Kennedy Space Center, where we do a lot of these kinds of studies. We have chambers where we grow lots of different kinds of plants. So in this project, our plan was to compare microbial levels of controlled environment grown produce with comparable retail produce and the reported values in the literature. The establishment of a baseline for expected microbial levels found on fresh plant foods will be used in a risk assessment and the development of microbial safety recommendations for these types of foods. Results from this work will help drive requirements for future food systems development beyond ISS missions. We've been looking at food safety of space-grown produce for quite some time, starting with the Russian Lada vegetable production hardware. This picture shows a mature crop of Mizuna, but currently our focus is on what we're growing in veggies. So this picture shows the first harvest and consumption, or the first consumption of a harvest of outrageous, which is a red romaine lettuce. And you can see the astronauts are kind of making a toast with their lettuce leaves. So since that first lettuce meal, they have enjoyed Chinese cabbage and Mizuna. And the future crops, we now have a variety of leafy greens that we're testing in chambers, and they're being flown and installed into veggie. We have plans for tomatoes and peppers. But with each of these different types of produce, they have to be evaluated for microbial food safety. So table 1 shows the bacterial and fungal counts from these older harvests from Lada and some of the first veggie red romaine lettuce. And you can see the numbers highlighted in red exceed what we kind of loosely use as a guide. And these are the NASA standards for non-thermostabilized food requirements. So what has become quite obvious is that these standards are not really applicable for produce. The aerobic plate counts, which indicate bacterial counts per gram, are usually higher when you're looking at plant material and produce. The Enterobacteriaceae, members of that family are indigenous to plant material, so you will find those anyway, and it doesn't necessarily indicate contamination. And then we do screen for pathogens that shouldn't be there, like salmonella. The yeast and mold counts are oftentimes higher. Also, you can see that in the numbers highlighted in red. So this project then had 3 components where we did a pretty complete literature review to look at what values are reported in retail and farm produce similar to the types that we're looking at. We also sampled market produce, which I'll talk about in a few minutes, and then also produce that was grown in our controlled environment chambers. So this summarizes some of the data from the literature, and you can see the ranges for these sources of lettuce: field, hydroponic, retail lettuce, and then bag lettuce, which I'm assuming would be minimally processed and probably washed. The ranges of the bacterial counts were kind of the 10 to the 4th all the way up to 10 to the 9th CFUs per gram. If you compare that to what we grow in veggie, this shows outrageous red romaine lettuce from a couple of tech demos. We're within that range and actually an order of magnitude lower at the higher level. So you see the same trend with yeast and mold. There's not a lot of difference between what's sampled from the field and what you find in the store. It's kind of not out of character to find some E. coli occasionally, and these coliform counts are pretty high on the high end, 10 to the 7th to 10 to the 5th. And then again, comparing that to what we get from veggie, we have yet to date detected any E. coli or even coliforms. And then we wanted to look at what's out there for other leafy greens, since we're kind of expanding the varieties that we're growing in veggie. Each type will have kind of its own microbial load. So the mustards are a little higher than lettuces. So Mizuna is in the mustard family. And we're looking at things like arugula and pak choi and some of those different types of leafy greens beyond just lettuce. So in the literature, that's kind of that same range, 10 to the 4th to 10 to the 8th colony-forming units per gram. And our Mizuna, which this includes both veggie and monogrowth Mizuna, are kind of order of magnitude lower than what you might find in the range found in the literature. Again, we have not detected E. coli or coliforms in those samples. So another component of this project was to sample retail market produce and just get some idea of what the microbial load is after you bring it home and wash it with water. So we chose crops that potentially could be grown in veggie or are already being grown in veggie, like the red leaf lettuce is comparable to our outrageous variety of red romaine lettuce. Cherry tomatoes. Curly mustard is kind of an analog for Mizuna. It falls in that mustard family. And then radishes and green bell peppers. We collected samples in triplicate from 3 different store brands over 2 consecutive, month intervals. And we also chose products that were as minimally processed as we could find. They weren't pre-washed. They probably were rinsed off but not washed and bagged. And also we chose non-organic produce just for consistency, because there can be differences between organic and non-organic produce. We wanted to compare what we see in the literature and what we find on the market produce with what we grow in our controlled environment chambers, which is a pretty clean environment for the plants. So we grew our Regis lettuce, which is grown in veggie. This is the Mizuna that's been grown in veggie and harvested, and we have an experiment planned for next year. These are the Pompeii green peppers. All of these cultivars were down selected from 5 or 6 different varieties for their horticultural success and also their small size and taste. And some of you at JSC are involved in those taste tests. This is our red robin variety of tomatoes, and then cherry bell radishes. So again, these were grown under ISS-like conditions, which is 50% relative humidity, higher CO2, 3,000 ppm CO2. These are kind of in the range of where the conditions are on ISS. 23 degrees C, the lighting intensity is about 300 microvolts per meter squared, and then we use the growth medium similar to what is used in the veggie pillows or ponds, which is the rooting container. It's a clay material. We autoclave it, and it has a crop-appropriate time-release fertilizer. The plants are sub-irrigated with deionized water. And then in our data set, we included some of the veggie analog experiments we've been doing, as well as some of the crops that have actually been grown in veggie on ISS. So this picture shows a Mizuna experiment. You can see there are different lighting treatments, and that is what this experiment was, to select the best LED lighting recipe and the best yield and the best horticultural outcome. So these are in an analog version of what we call ponds. So I'm not going to go into details about veggie too much, but there are two kind of containers that hold the rooting medium, the arsenite and the Nutricoat. Currently, we're using, you can kind of see it here, they're pillows. So when I refer to pillows, that's what we're talking about. They're just little bags. And there's a wick, and that's where the seed is. There's a new design called PONDS, and that stands for Passive On-Orbit Nutrient Delivery System, which is being re-engineered because there were some issues with water delivery. It has flown, but it needs to be redesigned so that, you know, the water issues are worked out. So, but we've done a lot of analog experiments with this PONDS. So that's included in our data set. From the veggie samples, we did our first mixed crop in pillows. The crop, and you can kind of see there's Mizuna here, and then the outrageous romaine lettuce here. We have a third lettuce called Waldman's Green. So this is the first where the crops were mixed in the same veggie unit. And then we had these are all tech demos. This one was to test a harvest method called cut and come again, which if you're a gardener, you know what that is. If you grow lettuce, you can cut some of the leaves off. You don't have to sacrifice the whole plant. So that's what cut and come again means. So, so some of that data is included in this data set as well. Because as you understand, every condition can affect the microbial load. So we want to look at harvest method, different lighting, even the location where they're grown. Our sampling and analysis included aerobic plate counts for bacteria. So if you see that on the next graphs, that refers to the bacteria colony forming units per gram. And then we do total yeast and mold count on inhibitory mold auger. We screen for specific pathogens, E. coli, Salmonella, Staphylococcus aureus, and Aspergillus flavus. And the data that I'm going to present excludes that pathogen screening because we haven't found any. So I'm going to talk about the bacterial counts and the yeast and mold counts and kind of where they fall with those different sample sources of produce. So on this graph, we have, in this scale, the Y scale is colony forming units log 10 per gram fresh weight. The samples are the market curly mustard. So this is just the Mizuna mustard. I'm going to talk about each individual produce type. The curly mustard, not cleaned and cleaned. Our chamber grown Mizuna, not cleaned and cleaned. And then we have the PONDS analog test and another analog with pillows. And then the Veggio 3D mixed crop Mizuna. So the cleaned produce in the chamber and market, these were triple rinsed with sterile DI water for 15 minutes each rinse. This shows cleaned Mizuna from this experiment. Those were cleaned with Prosan wipes. So Prosan is a vegetable wash. It's a lactic citric acid based cleaner. And they actually use these on the space station after they do a harvest. They take the wipes and pat their produce in between those two wipes. So the significance of these samples is that the microbial, oops, wrong way. The microbial counts On the market produce were significantly higher than the chamber-grown produce and the other analog tests, with the exception of the Veg-O3D Mizuna. So the Veg-O3D Mizuna is not higher, but it's right in there with the market produce. The same could be said for the yeast and mold counts. Now, looking at the outrageous lettuce, we have a few different samples included here. We have, oops, sorry about that, I pushed the wrong button. So the market lettuce, again, not clean and clean, chamber lettuce. This is the Veg-O3 tech demo where we did the harvest method. We got samples back from the second harvest and the final harvest. The samples we get back from the space station are frozen at -80, and we kept at -80, and we do the analysis in the lab. So it's really the only way to do live culturable microbiology on those samples. And then the Veg-O3D mixed crop lettuce. The differences in these samples were that Veg-O3D is significantly higher than all the other trials, with the exception of the unclean market. So just like with the Mizuna, it was up there with the market produce. And then both harvests of Veg-O3A are lower than the market produce, but they're kind of in line with the chamber-grown produce. If we look at the yeast and the mold, there is one change in that the last harvest of the Veg-O3A lettuce increased in yeast and mold count. And we see that with the cut and come again. With each harvest, the microbial load it doesn't every time, but it can increase. Okay, I better hurry up here. So with radish, I just show the plate counts. There's really no difference in radish. Radish has a high count. It's a storage root. It's in there with the moisture and the nutrients, so that would be expected. We included one data set from the Advanced Plant Habitat, which is plant growing hardware on the space station. They were doing some ground tests growing radishes, so we thought, well, let's see what it looks like as far as the microbe goes. And really, there's no difference between those sources of radish. And then with the tomatoes and peppers, we had the market and the chamber. The only difference with those was that the market averages were higher than the chamber-grown crops, and the clean chamber-grown crops were significantly lower than the unclean market produce. So in this case, the water wash seemed to work better in the chamber-grown produce. In conclusion, the number of bacteria and fungi on growth chamber and ISS grown produce are no higher than market produce from field settings. Produce sampled in the study indicated no specific microbiological risks associated with particular type of product. In general, the edible fruits, tomato and pepper, had the lowest counts, while radish, a storage root, had the highest, but that would be expected. A possible upward trend in microbial counts was seen with Veg-O3D leafy greens. This is where, we have to consider steps to minimize microbial contamination, such as increased decontamination of surfaces and the removal of dead plant material and any other unnecessary materials. Microbial monitoring of inputs into the plant growth system and the plants is important and should enable detection of any trends indicating increased microbial presence. For example, what we're seeing with this Veg-O3D, which is the most recent set of data. Defining risks and the development of standards and best practices for space-grown crops should allow routine, safe consumption of these items. And I would like to thank some folks back at KSE, Larry Koss and Tina Kodadad, for technical assistance, our interns who are great and accomplish tons when they're here, and then the JSC folks for their valuable discussions and input on moving forward with the microbial safety of space-grown crops. Sorry I went too long. Any questions?
Are there any questions for our speakers? Then join me in thanking all the speakers that we had today. Some great talks. If you think about any questions you have, our speakers are around. Feel free to go up to them and ask them questions. Thanks again.